Okay, I'm going to go through this because these are the numbers we're going to be working with today. This single phrase lets you make sense of just about everything in quality control. A number is a thing of awe. Each number either comes from opinion or fact. It tells you where you are, where you want to be, or where you expect to be. And if you can get each of those numbers into the right pot, QC makes a lot of sense. So where you are is the current mean, is represented by the current mean in SD. So my current mean is here, my SD is here. That's where I am now. It's a measured value where I am. This is the truth. Where I want to be is here at the true value, which is typically your peer mean for your QC sample. Within these lines is acceptable quality. Outside are your TEA limits. I like to call these failure lines. So you can say if I went over the failure limit, total error allowable sounds like a very, sort of, it doesn't sound as significant as going over a failure line, which is really what you're doing. So the measured mean comes from fact. You measure it. It comes from the instrument. It tells you where you are. The SD is based on fact. The true value is based on opinion, because you may want to get it from the peer report, or you may take it from the package insert, or you may have neither of those, and you may go back to your own history. So where you choose as the right place for your true value, or where the medical director chooses, these two decisions should be made by the medical director. Where do you get your true value? How do you select your total allowable error limit or your failure lines? These four numbers determine your analytical quality. You can crunch those four numbers down into one single number that you can look at, and if you know the margin for error, you know if your test is good, bad, or in the middle. As long as you have some margin for error, you're okay. You can still move before getting into trouble. So, which sample here has the least margin for error? If each sample shifts half its width to the right, which one's going to crash first? Whoops, sorry, I need to get rid of that. So this one, if it shifts half its width 2 SDs to the right, it's still good. But if this fellow performs the same shift, you're reporting too many bad results, because this method has better precision. So the size of shift, the margin for error that you have, is determined by both the width, the standard deviation of the population, and by the position, the bias. So those four numbers, and then we have to make 3 personal decisions in how you're going to monitor those for change. What you're going to do is monitor the mean in SD and make sure that your each value stays within the allowable error limits of the true value. So in order to do that, in order to detect change from that, you're going to set up a QC chart with a mean, an SD, and a QC rule. This is where it gets fun. Now we take it live. Okay, we are starting with a sodium. These are real numbers. So this was the peer mean for that month on their interlab report was 146. We're setting the allowable error limit at 4.0. The measured mean was 145.6. That's your measured SD. We can calculate the margin for error. Margin for error is the error you're allowed minus the error you've got, and divide it by the SD. You've got the number of SDs. Incredibly easy to calculate. You can have people doing this in their head with, all you have to do is add, subtract, multiply, divide. Our chart assigned mean and SD on this chart, on the chart on the left here, it is going to always use the real mean and the real SD. So this chart is going to use the real mean, the real SD. However, this one is going to vary with the personal choices. So right now, this is exactly how the lab set it up. So this is real. You have a measured SD of 0.99, but they've assigned it at 1.46. You know why they did that? They decided to assign their SD at a CV of 1% for every control. That's a new one, actually. I hadn't heard of that one before. So they I don't know. So people pick and choose where they assign means and SDs at random. There's no change in either of these, but look how different the QC charts look. See how this one, most people would say, oh, this looks better. This is exactly the same data. Both of these data sets have a mean of 145.6 and 0.99. Okay, now's when it gets fun. I wonder if David, are you with us yet? No, darn it. Okay, Rick, your turn. Change one of the four numbers.
Okay, let's change the measured mean to 147, say.
Okay, we're going to change
shift.
147. Now this is in a different, so this is if the method shifted up to 147, what you'd see is that this chart, because we haven't changed the assign mean in SD, so consider this again, we've got two charts. Now my measured mean is 147. My margin for error is 1.0. This method can only shift one SD before it's in trouble. Let me see if I can go back. What were we before? 146?
146.4. 3 or something.
4. Okay. The margin for error here is 1.6. So if this moves 1.6 SD, it's going to create results that go over the allowable error limit. Let me just show you how that would work. So if I shift this one 1.6 SD, 1.6 SD, I shift this method by 1.6 standard deviations, and now results are going outside the allowable error limit. So we did it the other way. So now, sorry, I want to show you this first. Okay, if this one shifts 1.6 SD, it will have results going over the allowable error limit. This is what you would see on the properly made chart. Several of the results would be flagged, and you would see more flags here than you would on the improperly made chart. In this instance, we had the mean assigned at 146, whereas here it's assigned at 146.4. I'm going to go back. I'm going to go back and shift the mean by 0 SD. So now we're going to go up here and put this to 147. What's changed is that the mean has shifted from where it was up higher. So now this margin for error tells me that it can only shift one standard deviation before it's in trouble. So it can only shift one SD. So Rick, why did the mean change? What causes that mean to change?
Technically, or
yeah, like, if you're running the method, you come in and oh my God, the mean has changed. What would you look for first? What's your typical causes of a shift in the mean?
Mechanically, it's a restriction in the sampling circuit. It's short sampling, for instance, and or it could have been short sampling when it was calibrated, and meanwhile that restriction is now gone, and now it's getting a much larger sample, which is causing your mean to shift upwards.
That's cool.
There's any number of reasons that can shift the mean.
That is really interesting because most, like and by the way, for those who don't know Rick, he is a service rep. So in the lab, you know, when all else fails, call service. So by the time he gets in to troubleshoot, everything else has already failed. Anna, do you want to give us some typical examples of what happens within the lab that would change the mean?
Oh, yes. When we have a shift in the mean, we're looking at a systematic error or systematic change. And a lot of times that's when we change lot numbers of reagents, when we calibrate. So anything that affects the specimens that are being analyzed in the same direction will shift the mean. And those are just common instances that occur in the laboratory.
Okay. Another question. When we look at quality control, there's sort of an assumption in the background of quality control that if a shift occurs, it's going to be a similar shift at both levels. We use the same control, most people use the same control rules for the same sample. And when you're picking and choosing rules, we work with an N of 2 or 3. But have you seen examples where one level shifts, the high level shifts and the low level doesn't, or the low level drops out of sight and nothing happens to the high level?
Mm-hmm. Yes, I have. And there are times, depending on what capabilities you have in the laboratory, if you can have you can select different rules at different concentration levels of your controls to monitor that way. But if you don't have that capability, if you're in a more manual system, then I would recommend just sticking with one QC rule that is a tighter control limit.
Yes, if you have to use only one, you would use the tighter one. If you can pick and choose, I would choose individually. Okay, we have, now our mean is shifted to 147. What are you going to do now? Are you going to change? You've still got a margin for error of 1. Your method is acceptable. Do you want to change the assigned mean to 147?
Well, I now have a new population from the old population. My old population had a measured mean of 146.4, I believe, and now I have a new population. So a new population is emerging. I would definitely want to make sure that I could link it back to the specific change. I would definitely begin looking at, was it a significant change? Is my total error now larger than my total allowable error? And if it's still acceptable, if I'm still within the performance requirements, then I want to make sure that my QC chart is in alignment with my current Gaussian distribution. So I would probably then recreate the chart so that my measured mean and measured SD is assigned to the chart.
Okay, I'm going to go back one more time and just do this simulation again. I'm going to make it a little bit simpler. So now we're at 146.5, which is about where we were, 0.99. I'm going to create a shift of 0.5 SDs, and that's going to take us up after it to, oh, I didn't say what it was afterwards. All right, I shifted the mean up half an SD, so it would go from 146 to 147. So that was the change that Rick said. He'd done something to the machine. It went from 146.5 to 147. So for one thing, that small shift, you're probably not even going to notice. The question is, was that shift significant? So what's going to happen with the properly made chart is with a shift of 0.5 SDs, you're virtually never going to detect that change. Okay, for the sigma files in the group, a margin for error of 0.5 is a sigma of 2.5. Although people say you should have a sigma less than 3, for the people that measure sigma, I've had some people tell me they don't stop until sigma is 0. So people have to realize where you are with your method. However, this method can still shift 1.5 SDs. So it shifted from here to here. We finally noticed it. We say, okay, it shifted. I'm getting more flags than I used to. Is it okay now just to change my mean to the 147?
Well, you have to be very careful, and you have to make sure that you can link it back to a known event and that it's still acceptable, where TE is less than TEA, and you might even need to adjust the appropriate QC rules. However, if you really do have to be careful, because you could also be masking a problem. So you don't want to just automatically change your chart just because something else has changed. You want to find out what caused the change and see whether it's a significant change or an insignificant change.
Anybody else got anything to add to that? Want to jump in? Okay.
I'm going to jump in for a sec.
Please do.
Okay, it's Mike.
Yeah.
And once again, this coming from the mind of a microbiologist and not as a chemist. But it seems to me that if you know, that must mean that some samples are have unexpectedly started to shift higher or lower than the and telling you that there's something wrong, and to just shift your curve to accommodate to that change is, as was just previously mentioned, it would seem to me to be a very dangerous thing to do. The point of the exercise here is to be looking for change, and when you start seeing change, to accommodate to it, but back into your is just saying you'll never end up seeing that there's a problem. You'll just keep on correcting for the problem. Isn't that true?
I'm going to jump in and play devil's advocate here for a moment, because we spend a lot of time worrying about change without answering that question, is it significant? If you can use these, if you get to see the analytical quality, the problem is the QC chart does not show you the analytical process quality. The only question that the QC chart can possibly answer is, has my method changed? It can't tell you if the change was for the better, for the worse, if it's acceptable or unacceptable. The QC chart alerts you to change, then you have to make the decision, is that change acceptable? To decide that, you need 4 numbers, my true value, my error limit, because if it's not within the error limit of the true value, it's not acceptable. You need to know where you are, so it's where I am, where I want to be. You can crunch that down into one number. That one number tells you can still move 1.5 SDs before you're in trouble. This method is not being flagged right now. So if it shifts, if the mean shifts now to 147, do I really have to stop and investigate when that, so if I say, oh, well, I know I changed a reagent lot, sometimes, in my experience in the lab, things just happen. I can go up here, I can change that mean to 147. Oh, okay. Now it's stable again at 147. This chart, the properly made chart, again I put the real mean, the real SD on it. If I'm over here, the question becomes, what am I going to do? Where did that 146 come from, and where did that 1.46 come from? So if I'm looking after assigning and it's not going to be automatically assigned, I would go back in here and I would change that, or consider changing. I don't know where they got that 146 from to start with. If they go in here and put the real mean on the chart, they're you know, they think they're okay, but now if it shifts, what do I need to go? Go 1.2 SDs. This method has failed. This method is reporting results outside your allowable error limit, and the odds are slim, even with a properly made chart, that you're going to detect that change. And with your chart the way they're making it, you're probably never going to detect the change. So I have a method now that's operating. If it went up from 147, it was up now to, let's say, 148. What do you want to do to improve that method? Darn it, David, you're not with us, are you? Anna, what are you going to do to make the method better?
Well, I'm going to first find out what's going on. And I'm going to be reviewing my documentation very closely to see if I can start linking a change to an event.
Okay,
So depending on
invent one change. Say it was this. Then what would you do?
Well,
actually,
again,
let me change the scenario. It wasn't
right.
a change. You walked into a lab and you're going to advise these people, is their sodium okay or not? You're going to look at this and say, yeah, your sodium is barely making it. If anything went wrong, you know, you would never know and you would report bad results. What would you have advised them to do in order to get away from that danger, to get away from the risk? How can they improve the method?
Well, first of all, we need to stop testing because we are having the possibility of reporting erroneous results when you have a margin of error of 0. So we need to really just stop testing there and find out what's going on. The other thing I would do is, again, find out what is the cause and begin addressing the issues, and then once those are addressed, then I'm going to load up on QC so I can have enough of a history to start figuring out where I am with the method, where I am with this current situation, and then create the appropriate Levy-Jennings chart that reflects the current Gaussian distribution so that I can effectively determine if my instrument remains stable or unstable based on the rules that I've selected. But right now, if I walked into this situation, I would say stop. You know, because no result is better than a wrong result, and we're now crossing the total allowable error limits with our results. So we're beyond specifications.
Okay, I'm gonna lead you a little bit further. If you could change one of these 4 numbers, which of these 4 numbers would you change? The true, the TEA, the measured mean, or the measured SD? If you could do something to change one of these numbers, which number would you change and how would you change it?
Well, after I ensured that the true and TEA limits were valid, then I would want to start looking at my mean. My measured mean is off, so I would want to begin looking at how I can address it, probably perhaps even calibration at this vague of a juncture as to what the specific problem is, but something so that my measured mean is closer to the true value.
Great. So I can go in and I'm going to recalibrate or change my reagent lot or call for service, and I'm going to bring that mean back to 146. So it's these numbers. So I can reduce the bias. Now I've brought my margin for error all the way back up to 2, which is still not good. Then I can look at what people are doing, and if we can improve this standard deviation. Now, sodiums are really cool. If you look around at real examples of sodiums, you'll see SDs anywhere from 0.5 to 2. If I can bring that SD down to 0.7, now look where I am. I've got a margin for error of 3.7 SDs. I'm still getting a sort of meaningless picture on this chart. It looks as if I have a negative bias when I really have 0 bias. And again, that's because this assigned mean and SD have nothing to do with reality. If I have the real mean and SD on the QC chart, well, the method is really, really good, but I'm still paying the price of these 5% false positives. This is where you can come over and say, okay, if I know the margin for error, then it makes sense if my method can shift more than 4 SD, I can use a 1 3.5 S rule, test my samples routinely, have the supervisor and the front line look at it once a month, and everything's fine. As my margin for error gets lower, I'm going to decrease the rule that I'm using. So working with a margin for error of 3.7, I can come right up here and use a 1 3.5 S rule. I'm going to go back over here. I can change that rule, and so what I'm going to do is I'm going to make a change of the assigned mean, the assigned S, or pardon me, I'm going to change the rule that I'm using on chart A. So instead of using a 1 2S rule, I'm going to go in and use a 1 3.5S rule. What that has done is it's gotten rid of all my false positives. But now you're saying, oh my goodness, you know, with 3.5 SD set as my QC rule, would I ever know if a real problem occurred? Well, let's go back in here. My margin for error is 3.7. If the mean shifts by 3.7 SD, then results will start to go over the allowable error limit. Even with a 3.5S rule, I'm going to see that in the first run. But, and again, this started as a real example, the way the lab was happy to set their chart up, if this method failed, you would just keep on reporting forever.
So it's really important that it begins with the right chart. And we really need to, I mean, when the system is stable, it produces a Gaussian distribution. And it's that Gaussian distribution that needs to be reflected onto the chart so that we can see if another population is emerging, and that's detected through the appropriate rule selected.
Yes, and that's exactly what we're dealing with here is two populations. When this population changes to become this population, then you see here, this population has a different mean, a different standard deviation. So this is the new population here, and the old population will have no results outside 3 SD. So anything that's outside 3.5 SD, you know is for sure part of this population. And that's the whole trick, really, is the overlap in between the two different populations.
But a lot of people are concerned about having such QC rules to alert them to a significant change. The other thing that we want to bring in mind is that not just plotting QC data, but there's also periodic review. When you review a chart, when you stand back and look at a chart, you can see a lot of shifts or trends visually very quickly. If it's not a significant change, I would still start looking into it, but I have the luxury of continuing to look into it while still reporting my patient results. So I get to pick the time we go down and address something before it becomes significant, as opposed to waiting until it does become significant and then coming to a complete stop. So this periodic review is also essential. You pick up the problems very early as well, and not just rely on your QC rules.
Anna, that critical point of, is this change significant? How should people answer that question? How do you answer the question, is this change significant? Because we want people, that's the critical thing. You know, your QC chart says my method has changed. The next question is this change acceptable or not? Does this change put patients at risk? So how would you answer that question?
Well, in a way, we have it backwards. We really need to define what is the quality that's required so that the test is clinically useful to our providers. So we first need to define what quality we need to provide, and then see where we are, and then determine, are we providing that quality? So the first place to begin with is define your quality requirements.
You really, yes, it's these 4 numbers. If you don't know the value you should get, you can't possibly measure accuracy. You know, bias by definition is the difference between the measured value and the true value. If you haven't set a true value, you cannot measure accuracy. You go into most labs, say, what you doing QC, what are you doing it for? Measure the accuracy and precision of the method. You say, that's cool, what's the true value? And they look at you like you've just dropped in from Mars. They think they can measure accuracy without ever setting true. So,
well, many people are under the mistaken idea that the mean assigned to the chart is the true value. No, that is the mean that is produced by the analytical system at that point for that specific Gaussian distribution. It has a unique mean in SD. That's what we need to capture and put on the chart.
And the problem is that the mean and SD that are on the chart are so often not the real ones. This is the crux of what's going wrong in quality control. All these bad habits have just slipped in over the years, and they've become the norm. Ever since we got computers and people had the ability to just change that SD and make the world change, they started messing with it because they didn't really realize what it was. Every lab I've ever been into, like, they do not assign their actual SD on the QC charts. This was 22 labs, 8 tests in the year 2000. All of these are higher than the real SD. All of these are lower. Whoops. No. This was the same thing in 2013 at 22 analytes, and they're all higher, the SDs. And this was a similar study in 2012. When you lie to your QC charts, they're going to lie to you. These personal choices that people make have a real impact on what's going on. And there's really only one proper way to do it. They not only influence the patient risk, but they influence your false positives too. This method was clinically acceptable, and yet this is what people were seeing. If we look in detail at quality control, it can be so much more effective, and that's one of the things that EP23 is going to ask, is verify the effectiveness of your quality control. Well, I had fun. I like working with these simulators. I have found that these, for the students, make all the difference in the world. When you can go in here and just change the SD and see what happens, it makes a big difference. And you can go in here and you can change your decisions, and you can drive what goes on, and that puts people in charge of QC. When you're practicing QC, you see so few failures. And part of the reason is you don't see them when they do occur, and the other part is that they're rare. We need to work with something like this so that people can visualize what's going on, what would happen if the method failed. And eventually we're going to get into software like, do I have it here? This one that will actually just tell you need to improve both accuracy and precision. It will show you the overlap between the good and the bad, give you a rating for your analytical quality, tell you need to review, tell you need to stop and fix your QC. A lot of the interpretation that we're passing on to people, the logic that interpretation is following can be put into the computer, and the computer can give us far more meaningful information. Instead of teaching 300,000 people how to interpret statistics, teach one computer. Okay, I am going to open it up to panel discussions if people have parting words. Go around. Anybody got anything to add? I hope we're opening up some interesting aspects to quality control that perhaps people have not thought of before. I hope we're moving towards a better, simpler way to do QC. I think there's a way to do it much more simply. Personally, I believe you can do QC without ever mentioning Gaussian distribution or QC rules. There's a way to put it all in the computer. You say, where do you get your true value? Where do you get your allowable error limits, and how many bad results are you willing to report? And with those three decisions, you can virtually automate quality control. On those futuristic words, I'm going to end this evening or today and say thank you very much, everybody, and hope to see you back here again in 2 weeks.